Okay, we're nearly at the end, guys. Magnetism is an important concept that we all must know. And it is kind of related to what we were talking about earlier. So what is magnetism? It's essentially the effect observed when a north and south end of a magnet attract or repel a neighboring ferromagnetic item. As we know from GCSE, opposite poles would attract and like poles would repel. And that is why when you freely suspend a magnet, for example, in a compass, it would align itself to the north or the north-south direction of the Earth's magnetic field. Fun fact, the Earth's magnetic field protects us against harmful radiation. So thinking about what ferromagnetic materials are, so for example, iron shavings, iron filings would be a good example. So in these kind of materials that are easily magnetized, they have lots of different electrons. These arrows kind of represent the spinning electrons. And in most objects which aren't able to be easily magnetized, the spins of the electrons are paired, and so they cancel each other out. Whereas in ferromagnetic materials, they are not paired. And therefore, if they are physically near to a magnetic field, they become increasingly aligned. So they go from the left to the right. So they become aligned in the direction of the magnetic field or the magnetic domains. If the level of applied magnetism, which is denoted by H, then the domains can actually become irreversibly aligned, and so it just becomes a magnet and it can't be undone. Also, permeability affects the way that a material responds to a magnetic field as well. So the more permeable a material is, the greater it will respond. And that is why metals like iron, which are permeable, respond more to magnetic fields than air, for example. So how does it relate to electrical currents? So basically what I was saying earlier, where a magnetic field is induced around a conductor which is carrying an electrical current. And therefore, magnetic fields can be created using electrical power, and then that can actually be used to provide a mechanical force, for example, in an electric motor. So the magnetism kind of moves the motor around. And also it works the other way. So if you move a wire through a magnetic field, an electric current can be induced that's proportional to the speed of the movement. So obviously in the Earth's magnetic field, it's just not strong enough to do that. But essentially it's a way in which mechanical force and movement can be transformed into electrical current. So then there's this idea of magnetic flux. So the lines of magnetic flux can be seen in this picture, and they represent the effect that a field has around a magnet. When the lines are drawn closer together, the flux density is higher, and flux density is essentially like the strength of the magnetism, and therefore a current is induced. The current that is induced is greater when the flux density is than when the flux density is low. So, for example, the Earth's flux density is low, and that's why we don't create currents everywhere with wires. This is just an equation that relates the force experienced to the electrical charge times the velocity times the flux density, which is measured in Tesla. So that's where we learn more about that from apparently. Okay. Another concept to know about is hysteresis. So it's basically where if you remove a magnetic field, sometimes the flux density doesn't actually return to zero, and so the material remains weakly magnetized. And so this failure to return to an unmagnetized state is termed hysteresis. This is a curve of hysteresis. So as you can see, starting at the origin, as you apply a magnetic field, the flux density increases to this point, 1. But then as you remove it, it actually kind of declines at a slower rate, and it actually crosses the midpoint at a higher flux density. And so it remains slightly magnetized. So you have to actually put an opposite force you have to apply an opposite force to get it to reverse, and then it will complete the loop. The area of this loop represents the energy lost when you magnetize and demagnetize something. So this is the same concept we were talking about earlier. As we know, coiled wires have a more intense magnetic field because of the proximity of multiple magnetic fields. So this is similar to the idea of an inductor, or it is the idea of an inductor. That's what it is. And also the number of coils is proportional to what the flux density is. So the flux density will increase depending on how many coils you have. And again, we were talking about different materials that you can have as sort of the core of the coil. And so iron has a higher magnetic permeability, so putting it on an iron core will increase the flux density. Faraday deduced that the voltage induced in the coil is obviously proportional to the number of turns in the coil and also the rate of change of magnetic flux. So how is this all relevant? So essentially, this concept allowed us to create the first transformers. So you have an iron core here, and you have one side with a wire, a coil around it, and then the other side with a different coil. And there is actually no connection between the two apart from through this core. And this is the first transformer. There's no electrical connection between the input and the output. And this essentially allows you to increase or decrease the voltage. So if you have a higher number of coils on one side and less on the other, then you can kind of step up the voltage. So that's how you can transform energy from one way to another. There's also a concept of isolating transformers, which is important for us in theatre because it allows us to isolate an entire operating theatre. Or an individual instrument, and it basically increases safety. Cool, so quick knowledge check. Can anyone tell me what happens when two electric coils are wound around the same core? I'll let you read the options. And maybe Gautam, you go. What did you say?
Said false for the vote. Over enthusiastically.
Yes. I actually just had one right answer here. Sorry, guys, I should have explained that a bit better. So, but that is correct. So this one isn't true. It doesn't form an electrical connection. There's no need for that because of the magnetic connection. But it does induce a magnetic flux in the core. So that is correct. Okay, this one's a true false. So now you can get excited, Laura. So, which of the following statements are true or false related to the properties of ferromagnetic materials? Do they have paired electron spins? False. Yes. Do they have unpaired electron spins? Yes, they do. Do they have microscopic domains containing random magnetic fields? Yes, they do. Are they reversibly magnetized? Yes. So as I was saying earlier, they reach kind of a saturation point where they become a magnet and they can't be reversibly magnetized. And finally, do they require an electric current to magnetize them? No, that is cool. Okay, last bit, guys. But annoyingly, this is one of the most important bits, but kind of the most boring. So electrical safety is something that they like to quiz us on in the FRCA. So let's learn about it. So electrocution. These are the kind of levels that cause different impacts on the human body. So a 1 milliamp will cause a tingling sensation. Over 15 will cause, well, you might not be able to let go, and then that might cause death by asphyxia. But you'd need over 75 milliamps to cause VF, which would result in rapid death. And this is just a bit more of a detailed explanation. So, for example, 15 would be severe pain muscle contraction. So we wouldn't tend to go anywhere near that, whether we would the nursing note or something like that. I think just because, yeah. So James was asking how does it cause asphyxia, and essentially it means that you cannot breathe properly, and you're unable to let go to release yourself from the current, so you just suffers with oxygen. Yes. And also different biological tissues have different electrical resistances. So for example, soles of our feet, if we have callousy feet, which I do, then that actually provides quite a lot of protection. But once the skin is breached, it becomes much more vulnerable. So later on, I think I mentioned about the, when you're in the cath lab, for example, you are actually a lot more vulnerable because you've put catheter right inside the heart, which is a lot more of a conducting material. The harmful effects also depend on the duration of contact as well as the magnitude. And the frequency of the current may also impact the likelihood of VF. So 50 to 60 hertz frequency is sort of the magic number for VF. Okay, classification. They do like to ask you about this, apparently, in the exam. So I know you were saying about this. There's two different types of classification, starting with class 1, 2, and 3. So class 1, which is denoted by this image here, is basically where the live and neutral wires, which are mains powered, will be enclosed in a metal case, and this metal case is then earthed. So this symbol is like the earthing symbol, so that's kind of the best way to remember it. The return earth pathway is linked to this neutral star point, which basically is a safety mechanism to prevent it from going through the patient's body or from electrocuting you. And also it contains a fuse which will melt if there's a leakage and it becomes too large, and then that will cut the circuit as well. Class 2 has this sort of double box symbol, which is quite easy to remember because it's also known as double insulated appliances. So an example of this would be a phone charger. If the case is plastic, it's likely to be a class 2 appliance. And essentially, the double insulation reduces the chance of you electrocuting yourself. But there's no earthing involved in this one, so it's not necessary to be earthed because it's doubly insulated with a special material. And then finally, class 3, these are items that are designed to be supplied by an extra low voltage power source. So for example, laptops. There is again no earth conductor, but the voltage should be low enough that if a person touches it, comes into contact with it, it shouldn't actually cause electrocution. And then there is further classification of medical devices, so type B, type BF, and type CF. The type B may also be mains powered or internally powered, and may also have the same safety features as I mentioned in the last slide. But they have different maximum allowable leakages. So, for example, the direct current, the leakage is 50 microamps for a single fault, 10 microamps with multiple faults. But with AC leakage, it is quite a lot more. This is symbol for type B devices. Type BF, so the F stands for floating. And so it basically means that all the patient connections are isolated from the other circuits. And that is a safety feature again. But the maximum allowable DC and AC leakage is the same as the type B circuits, but it is safer because of the floating element. And even when 110% of the main voltage is applied, it actually never exceeds the maximum allowable leakage because of this isolation. And then finally, so that's the symbol for the BF, and then CF is basically a device that can maybe connected to the patient's heart. So this is the symbol. That's quite easy to remember. It's like C for cardiac. And again, it's an F type, so it's a floating circuit. As you can see, the maximum allowable leakage is a lot lower, even when mains is connected. So this makes it safer for an internal device. So how can electrocution happen? So just moving back to class 1 devices, there were 3 different safety precautions. So all 3 would have to kind of go down in order for you to be electrocuted. So you either have a faulty monitor with a leakage current to the case, a fault in the monitor earth lead, and then the combination of those means that the earth lead would then become live. And then the circuit through the patient is like a complete circuit then, and the current will flow through the patient instead of down into the earth. A way in which they sometimes make devices safer is to earth things separately. But a problem with this is when the earths are not sort of calibrated at the same zero, so there's still a potential difference between the two earths, and so you can still get electrocuted. Okay, so just bringing back the concepts of the capacitors and inductors. So capacitive coupling is where so an example of this is an ITU, where you have a neighboring unconnected device. The patient kind of acts as the other side of the capacitor plate, and so it would behave like a capacitor in which the unconnected device has a current flowing through it, and it induces a voltage in the patient. I don't really know how that works, to be honest, but that's what capacitive coupling is. It's almost like the patient becomes part of the capacitor. Inductive, I'm not sure if this actually happens very often in real life. I don't think it does, but it's a concept that you need to know about. Inductive coupling is basically where a neighboring device, such as a lighting circuit, may induce a current flow via its magnetic field. So it's again almost like the patient is the inductor. Does that make sense? So how do we improve electrical safety inverters? There's a number of ways. So isolated circuits, which is something I mentioned earlier. So the patient is not earthed at all, and we don't need to worry about the two earths being calibrated together. There is current operated leakage circuit breakers, which are a bit like the fuse I mentioned. So if the fuse melts, then the circuit will stop running. Double insulation, which is what I mentioned before, and then just lower voltage equipment as well. So this is one of the safety mechanisms I mentioned. So on the left, this is domestic classified equipment, which is actually thought to be quite unsafe, because if you touched a part of the circuit, then the circuit would flow through you and into earth. Whereas for a lot of medical devices, we have this non-earth isolating transformer, and you can see the difference between these two. So if you touch something, no current would run through because of this insulated bit, or it's isolated from the mains. And so this is safer because there's no return pathway through the patient. Circuit breakers. So you can see from the image that there's two pathways here, L and N. In the absence of any faults, the two currents through L and N would be the same, and therefore there would be equal and opposite magnetic fields in this toroid transformer. But if there is any current difference, then it causes a current in the toroid, and that would actually open the switch and disable the circuit. So it's again a bit like a fuse that kind of is there to just in case something bad happens, and then it's like an up switch. You'll be glad to hear that I didn't bother doing any MCQs for that bit because it's so boring. But these are my resources, mainly e-learning for healthcare. I think I did Google a couple of things as well, such as BBC.Birds and stuff. But if you have any questions, please do let me know. I may not be able to answer them, but also e-learning podcast is really good. And there is extra questions on there if anyone wants to enlighten themselves. Great. So that is the end of electricity and magnetism.